Okay, so now we're going to talk about limits, which is a natural topic to discuss after explaining how to find domains of functions. Again, in the same way in which for a function of one variable, the domain is not very interesting because it's basically like a bunch of intervals. When you are trying to study the limit of a function of several variables, that's a lot more complicated than just the ordinary case of a function of one variable. If you had a function of one variable, right, then say if you wanted to study the limit here, well, one way to think about it is that the limit would exist, right, as x goes to a of f of x, would exist if the two lateral limits exist, which were the limit as you move towards a from the left, and the limit as you move towards a from the right. Okay. On the other hand, now when you have a function of, let me just call this y equals f of x. When you have a function of several variables, then the graph looks like a surface. And then when you have a point here, say a comma b, maybe you want to study something as the limit as x comma y approaches a comma b of x comma y, f of x comma y. But now the issue is that there are many ways to approach this point. So for example, you could approach this point through a straight line like this one, but you could also choose another line approaching this point. In fact, you don't need to approach it through a line. You could also approach it through this sort of more sinusoidal curve. You could also do more weird stuff like spiraling towards this point, like this. And so the point is that instead of lateral limits, in a sense, we would like the limit to exist if for any possible trajectory that is approaching that point, the corresponding limit of the function would exist. Okay, so in a sense, it's a lot of a tougher constraint to a lot more difficult condition to satisfy than just like the ordinary lateral limits to be the same. So first I want to do an example where you can see that what sort of things you look for in order to decide if a limit exists or does not exist, and then in the next video we'll use some techniques to find limits, like basically like the squeeze theorem. There's like a standard definition of, in terms of epsilon delta definition for a limit, but really we won't spend too much time talking about limits, and so you can read about it of the book, but it's not I mean, it's a lot more technical, and we just want like a big picture of what you should expect. Okay, let's analyze this example. Let's say that you were trying to understand the following limit. So a limit as x comma y approaches the origin of, say, x, well, xy times x plus y cubed. Okay. Now there's a notion of, okay, so this is similar to the limits that you had studied in calculus 1. So for example, if this had been like the point 1, 1, then in order to find this limit, this function is basically continuous. So in order to find this limit, you would just evaluate, substitute x and y with 1, and so you get 1 times divided by 1 plus 1, which is 1/2, and then you would say that the limit is 1/2. What makes this a particular case of a limit is that, right, if you just do the naive thing of evaluating, you get 0 over 0, right? And that's exactly the sorts of limits that calculus is all about, right? That's like basically the format of a derivative as a limit and other things. And so it just means that we cannot just naively plug in the numbers, okay? And also you have to come here open-minded, so you cannot just a priori know for sure whether you should expect this limit or not to exist. And so, like, one way I like to think heuristically about trying to come up with an answer for whether or not there might be a limit, it's just like in terms of like orders of magnitude. So like what sort of the dominant term in each of the corresponding summands or factors that appear in this expression. So for example, if you look at the numerator, right, imagine that x and y have units of length, right? So the numerator has like units of like units of length squared, right? Which again, you don't need to think of them as length squared, but it just means that it's like some sort of quadratic power, right? Because you're multiplying two quantities, so it's like a quadratic expression. Okay. On the other hand, the denominator the denominator is this term is sort of linear, and this term is cubic, right? So there could be trajectories that you choose where one of these two is more dominant than the other. So it's either behaves like morally either linearly or in a cubic way. Okay, and so what we want to see is so if this is sort of quadratic, if you divide something quadratic by something linear, right, something like area by length, that just gives you units of length, and so you would expect that to go to 0. On the other hand, if you divide something quadratic by something cubic, you get units of 1 over length, and as the length goes to 0, you expect that to explode. So there seems to be like situations where you might expect this limit to go to 0, and others where you expect this limit to blow up. So based on that, you might think, oh, the limit does not exist. Okay, and so that's what we're going to try to investigate. Notice in particular that the domain of this function, right, it's just all the points x comma y which are not the for which right, you can use any point that where x plus y cubed is not 0, right? And so, well, let me just say, let me use basically what's the same expression, but maybe it's easier for us to understand. So again, as I mentioned before, how would you plot the domain of a function? Well, you first plot the equality. The equality here would be x cubed plus y equals 0. Which is the same as y equals minus x cubed. And so that looks like, again, maybe I should put like a minus here, just to make it easier. So that is just y equals x cubed. If you remember the graph of y equals x cubed, it looked like this. So I'm making this as a broken line because that means that this is precisely where the function does not behave nicely. Meaning that any other point, like in order to study the limit at the origin, you can choose any curve where, as so long as it's different from this forbidden curve. Because on the forbidden curve, the function is not defined. But for the others, you can just see what happens. So again, just don't use the curve that's where the function is undefined, but any other curve is allowed. So I mean, you can just start slowly and just see what happens if you choose either the y. You could approach this point from the y or x-axis. Alright, so what happens if you approach this point moving along the x-axis? So the x-axis means that y equals 0, right? And if you put y equals 0 in this expression, well, xy over minus x cubed plus y will become 0 over minus x cubed, and that just becomes 0. So if you just move along the x-axis, the limit will be 0. Along x-axis. Which means that if you were a particle moving along the x-axis, and you could only think of this as a quantity that you're trying to measure, your prediction for what the measurement should be at the origin is that it's 0. Something similar happens if you take, say, the y-axis curve, because now x equals 0, and then here, again, the limit is 0, should be 0 now along the y-axis. Okay, now, so clearly this is suggesting that at least some limits are 0. The next step to try, like just because two limits are 0, that does not mean that the limit has to be 0 all the time. That's the issue here that we are facing. We need like either find a trajectory for which the limit does not yield 0, or try to show directly that the limit will be 0. But in this case, actually the limit will not be 0, so we just need to keep trying harder. So let's just take this heuristic about the, well, maybe I should not, yeah, let's just keep, again, we cannot use the trajectory which is, we cannot use this trajectory, this is forbidden. We already used this one, we already used this one. Now let's try to move along as a line, not which is vertical or horizontal, but that has some slope, and see what happens. So if you try y equals mx, what happens in this expression for the limit? You get x times mx divided by minus x cubed plus mx. And so that gives you mx squared divided by minus x cubed plus mx, and you can cancel the x, and so this gives you mx over m minus x squared Okay, and basically the limit of this, like now we're assuming that the slope is at 0 because we already analyzed this. So the limit as x goes to 0, right, as you're moving towards the origin here, as you move towards the origin, this just goes to 0 over m, which is 0. So it seems that any straight line that you choose will yield the limit 0. That's useful to know. But again, that doesn't mean that you exhausted all possibilities, because there are other curves that are not straight lines that you could try using. So in order to figure out what could be a good option, notice that the thing is that this kept giving 0 because you still had like an x in the numerator that could make things go to 0, right? So if we could only factorize, if we could kill the x in the numerator, we might be good to go. Okay, so that's what we need to see if it's possible. We need to sort of get rid of terms that want to go to 0 in the numerator so that we have a chance of succeeding. Okay, so here's the trick. So the issue is that so far the numerator has been winning, right? Because it has been giving you something that's going to 0. So what we want to do is somehow being able to cancel the numerator completely, okay? And the easiest way to do that is just to make the denominator, right, the same as the numerator. Choose a curve for which this happens. And you say, well, is this even possible, right? Like this seems suspicious. But then like the idea is like, this equation is the same as saying y minus xy equals x cubed, right? And then this is the same as me writing y times 1 minus x equals x cubed. And so y equals x cubed over 1 minus x. So I could have said, oh, choose this curve, right? And let's see what happens. But if I had done that, if I had started with this formula, then you would have been like, oh, what the heck, like, right, what is going on here, right? Like, why, like, how did you come up with it, right? And so I came up with it by just requiring the denominator to be the same as the numerator, okay? And so let's see what happens now. And this is a cool trick. So if you do this, then it's very easy to see what xy over minus xy plus minus x cubed plus y is. Well, that's just xy over xy. And that's just 1. And so the limit along this curve, so the limit along when y equals x cubed over 1 minus x, the limit is 1, which is not 0. And so we found a curve for which the limit does not work, does not give you 0. So that means that the limit does not exist. So this one does not exist because, which usually we just abbreviate as dne, because if you take a line y equals mx, the limit was 0. But if you take a curve, which again this is like a weird curve, if you take x cubed over 1 minus x, you get limit 1. Okay? And so that's in practice how you can find the limits of functions. So it takes some getting used to it, We'll do some examples later which are a bit easier. This is a tough example, but it's like as tough I think as they can get.